Hey everybody, how y'all doing? It is November 14th, 2020, our continuing voyage into the unknown, amazing, stupendously awesome world of the future. And we are continuing on from last week where we were discussing what it is about modern physics that has something to do with our lives, like what it is that helps to explain some of the things that we kind of know intuitively and that we see happen on a regular basis. And we just say, wow, gee, I guess I just guessed right. Or I guess, it was just meant to be. Or, well, gee, I really can't figure that out. And you just kind of step back and say, I wonder what's going to happen tomorrow. Well, there are some of us that are, I think, probably by way of being less frantically busy on a day-to-day basis, who have a little bit more time to reflect or meditate, or maybe even do self-hypnosis or something along those lines, transcendental meditation, whatever it might be, that feel that they get a kind of an extended knowledge about things, or they get a kind of a premonition, an intuition, a sense, a gut feeling, whatever you want to call it. I think that everybody listening and viewing with us would probably agree that from one time or another, you've had an experience where you just had a knowing about something. Well, there have been people who have pondered this for decades and centuries, and there have been physicists going back a good 6 decades, going all the way back to Niels Bohr, talking about phenomena that he observed. And I don't know if he initially observed it or whether he mathematically theorized it, but that there is an interaction between particles at smaller and smaller size that is not explainable by regular laws of time and space. And so we get into this subject that we've been in, and it seems complicated, and it really isn't. We've got a couple of people who are going to play a couple of videos tonight, short ones, and then discuss them. And what's the heart? Okay, these are the things that we're talking about. Quantum entanglement. What in the world does that mean? Or this other one. And if you read Scientific American or a few of the other journals, you're going to run across this pretty quickly. The other one that they refer to is spooky action at a distance. Oh, spooky. It's not spooky. That's almost it's incongruous action. It is something that just doesn't apparently look to you like it could happen, but it does. And that is exactly what happens when you get the feeling, I don't know if you've had it, but I have had it happen, where I just figure something's going to happen, like I just thought of somebody, and then lo and behold, 2 minutes later, the phone rings and it's them. And that's happened more times than I could, reiterate right now. Things like that. These are related to these spooky actions that we're talking about, these things that don't seem to obey the laws of cause and effect, direct cause and effect. I got to mute something. I just heard it go off. Hang on a second here. Okay, that should take care of that. So anyway, that's where we're going. And I'm going to put this thing right up there and say hi to everybody out in chat. I hope you're all doing great tonight. We're so glad that you're here with us. We all want to go together on this careening ride into the abyss of unknowing and come out of the other side of it knowing a little bit more than we went in. And it's just, wow, it's fascinating. So Lily, Rocco, Molly, everybody else out there, good to see you all tonight. And let me just get us kind of reviewed just a little bit from where we left off last week. And I'm going to put a share up here. TMC, how are you tonight?
I'm great, Andy. How about you?
I'm okay. Busy.
Good.
Just been so busy this week. It's been crazy. I'm just glad to be here, especially with you and everybody else. It's just so much fun, and it's so stimulating. It's so amazing. So we got this book that we talked about last week. I think I almost got it up here. Yep, here it is. Okay. Here we go. Except, why did it do that? Why did it do that? Darn it, Zoom's been working so well, and it's still working pretty well. Let me try that again. Okay, there we go. All right, so a gentleman by the name of Dean Rodden wrote a book, and it was a kind of an every person's review of entanglement. And entanglement is that physical property we've been talking about. And I'm going to go with just a couple of little parts out of it, and then we're going to move right on. Why do we want to talk about this? Because if we're ever going to reach the next level of conscious awareness of our universe around us, I'm feeling the more and more that I read about where physicists have gone and where experimentation has proven, and literally what we're even doing, what we're building with electronic circuits nowadays, as well as merging that together with an understanding of things that we don't have a rational explanation for, such as what we were just talking about. This is the direction that it goes in. So here he goes. And if you want to really go further into this, you can go back to last week's episode where we really went more into this. So I'll just go to the second paragraph. The deeper reality suggested by the existence of entanglement, which is one of these quantum phenomena, is so unlike the world of everyday experience that until recently, many physicists believed that it was interesting only for abstract theoretical reasons. They did accept that the microscopic world of elementary particles could become curiously entangled, but that these entangled states were assumed to be fleeting and to have no practical consequence for the world as we experience it. And guess what? That view is rapidly changing. That view has rapidly changed. And I think that it would really be safe to say, I'm sure that you'll agree with me, TMC, that the next generation of computer equipment that we have has everything to do with utilizing and exploiting the phenomena of quantum physics. That's what's going to bring computers to the next level. And when we get into multiple interactions of entangled computational parts, it's almost like the sky's the limit what the power of that type of an interconnected computer or group of computers could be that are all using quantum computing. It's absolutely amazing, because just at its simplest level, quantum computing is an order of magnitude greater in power than any of the best standard classically designed computers that we have now. And that's just computers. So keeping in mind that these quantum phenomena impact tremendously on the computer industry, and that the next generation of computers, they're already prototyped, they're already ready to scale up. And it has everything to do with that, plus explaining a whole lot about some of the further potentials of humans, our consciousness, our minds, and thought and perception at a distance. And at a distance, both in physical distance, like miles or perhaps even far further, as well as distance in time, either forward or backward. Amazing, amazing stuff. We kind of went into the foundational level of it last week, and we're gonna go further now. So this is why we want to understand more about the quantum reality that it appears more and more that we have actually been living in all this time, but we just didn't know it, because it's not something that you see when you look at it directly. It's not something that you're gonna immediately observe, just like when you get in your car and close the door and drive off. That's all physical. Eat a sandwich. It's all very, very tangible and in the real world. This stuff doesn't live there. It is there, but it's also elsewhere, and all at the same time. Sounds crazy, right? Well, the only way to get a handle on this is to start with some really simple explanations, and that's where a couple of videos come in. TMC, what do you think? Any comments so far?
No, I think you're doing good. I'm curious to see where we're going to end up.
All right, so we're gonna. I mean, it's not just for everybody out there participating, listening, and viewing with us to try to start off simple with this. It's kind of like it. For me, it's also rather complex. And I think I forgot to share the audio, so please stand by. Let me just put that share up again. Share computer sound. There we go. Check the box. And so all speculations from everybody participating out there with us, folks, you're part of this. We're all on a kind of a joint discovery. This is the Saturday night ship of discovery out into new understandings of amazing stuff. And it's kind of good to take a break from, the politics that's going on and all of that stuff. And I think at the end of it, if we were to really develop further understandings in these areas, we just might find that it helps to make us be able to put some of what currently is on our minds, maybe even stresses us out, into a better perspective, and maybe give us a little bit of relief for that just by virtue of having a better perspective of everything. So here we go. This is a very, very simple and well referred to example about quantum mechanics, and it is called Schrodinger's cat. Here it goes.
Consider throwing a ball straight into the air. Can you predict the motion of the ball after it leaves your hand? Sure, that's easy. The ball will move upward until it gets to some highest point. Then it'll come back down and land in your hand again. Of course, that's what happens, and you know this because you have witnessed events like this countless times. You've been observing the physics of everyday phenomena your entire life. But suppose we explore a question about the physics of atoms, like what does the motion of an electron around the nucleus of a hydrogen atom?
And by the way, just credit where credit is due. We put our disclaimer up at the beginning of this show. This is a re-streaming of something that was from a TEDx done by a man named Josh Samani. And this is done in a non-profit capacity for the purpose of education and spreading good knowledge for the benefit of all. So hopefully we're not violating any rules or terms of service by any of the platforms that we stream on. This is non-profit and for educational purposes. I just might let it go for more than 30 seconds at a time based on having made that statement.
Look like? Could we answer that question based on our experience with everyday physics? Definitely not. Why? Because the physics that governs the behavior of scales is much different than the physics of the macroscopic objects you see around you all the time. The everyday world you know and love behaves according to the laws of classical mechanics, but systems on the scale of atoms behave according to the laws of quantum mechanics. This quantum world turns out to be a very strange place. An illustration of quantum strangeness is given by a famous thought experiment, Schrodinger's cat. A physicist, who doesn't particularly like cats, puts a cat in a box, along with a bomb that has a 50% chance of blowing up after the lid is closed. Until we reopen the lid, there is no way of knowing whether the bomb exploded or not, and thus, no way of knowing if the cat is alive or dead. In quantum physics, we could say that before our observation, the cat was in a superposition state. It was neither alive nor dead, but rather in a mixture of both possibilities, with a 50% chance for each. Dead.
So there are other experiments which you can construct with apparatus that do not require the use of a cat and a bomb that also can prove this. So I want to replay this a little bit because he's speaking very quickly and you kind of got to let this sink in. It's all about there being two possibilities, and up until the next time frame occurs, you don't know which one of the possibilities it's going to be.
Quantum physics, we could say that before our observation, the cat was in a superposition state. It was neither alive nor dead, but rather in a mixture of both possibilities, with a 50% chance for each. The same sort of thing happens to physical systems at quantum scales, like an electron orbiting in a hydrogen atom. The electron isn't really orbiting at all. It's sort of everywhere in space all at once, with more of a probability of being at some places than others, and it's only after we measure its position that we can pinpoint where it is at that moment. A lot like how we didn't know whether the cat was alive or dead until we opened the box.
So, make any sense? Is it too much, too little? We obviously don't know what the state of something was. Something happened, and we won't know what it is until we go and look at it. And that's all that we're talking about here, assuming that we didn't know, between the cat and the stick of dynamite, what happened, assuming that we didn't know, we had no clue where the electron was orbiting the hydrogen nucleus until we observed it. Pretty simple, right? Well, once we grasp this principle, we can extrapolate from that out into many, many, many other events. We can construct other experiments which prove this out. And they've even gone so far as to design electronic circuits which exploit this type of phenomenon. So he goes, this is very short. We're already 2 minutes into it, and there's only a few minutes more.
This brings us to the strange and beautiful phenomenon of quantum entanglement. Suppose that instead of one cat in a box, we have two cats in two different boxes. If we repeat the Schrodinger's cat experiment with this pair of cats, the outcome of the experiment can be one of four possibilities. Either both cats will be alive, or both will be dead, or one will be alive and the other dead, or vice versa. The system of both cats is again in a superposition state, with each outcome having a 25% chance rather than 50%. But here's the cool thing. Quantum mechanics tells us it's possible to erase the both cats alive and both cats dead outcomes from the superposition state. In other words, there can be a two-cat system such that the outcome will always be one cat alive and the other cat dead. The technical term for this is that the states of the cats are entangled. But there's something truly mind-blowing about.
Now, he's going real fast. What we have observed, and well, not we particularly, but what has been observed in repeated physical experiments in physics, is that when two particles are generated, and they are generated in an entangled state, if we know the state of one of those particles, we know for sure the state of the other particle. The other particle is always in the opposite state. Therefore, if one of them, in the case of electrons, if one of the electrons is rotating clockwise, it will always be that the other entangled electron is rotating counterclockwise. We only have to measure one in order to know for sure what the state of the other one is. Notwithstanding the fact that the interaction between these particles in their entangled state defies the laws of time and the speed of light. It's instantaneous. Fascinating. So, got to keep that in mind too. So it's a little complicated, but if you really look at it simply, it's just we don't have a way to explain how this happens, but we know that it does happen. That's the whole point of it, because that's so much like so many of those experiences that people have in which they just have a knowing about something. They can't possibly explain to you how they know it, but they know it, and they're right more often than they're wrong. And they are related. And once again, you could refer back to last week's episode, and we gave some little bit more example from the human standpoint. But let's go forward with this little example. This The crucial part about this is that there is a relation between the two. That's the entanglement part. So it's almost done. Bear with us. This is good stuff. Back it up a little bit.
Term for this is that the states of the cats are entangled. But there's something truly mind-blowing about quantum entanglement. If you prepare the system of two cats in boxes in this entangled state, then move the boxes to opposite ends of the universe, the outcome of the experiment will still always be the same. One cat will always come out alive, and the other cat will always end up dead, even though which particular cat lives or dies is completely undetermined before we measure the outcome. How is this possible? How is it that the states of cats on opposite sides of the universe can be entangled in this way? They're too far away to communicate with each other in time. So how do the two bombs always conspire such that one blows up and the other doesn't?
So, comments out in the chat. Rocco has indicated half the cats are really pissed off. I gotta say, there are many other examples of a not so incendiary or such an emotionally charged nature for any animal lover to think of one cat blowing up and the other one doesn't. Many examples. I mean, Schrodinger chose to use this as the example, and it certainly does hit home in a ballistic kind of way. But there are plenty of examples of this, and we do it with electronic circuits too. So he's almost done. Here we go.
You might be thinking, this is just some theoretical mumbo-jumbo. This sort of thing can't happen in the real world. But it turns out that quantum entanglement has been confirmed in real-world lab experiments. Two subatomic particles entangled in a superposition state, where if one spins one way, then the other must spin the other way, will do just that, even when...
So bringing this to home, if you remember what he said, that this is something that these entangled particles could have that relationship, that entanglement, even if they are a great distance away, and it happens instantaneously. Now, this is where it ties into computers, the new types of computers that they're building, which is that we've had a limitation in computing power for a long time, which is the speed of an electron, which is the speed of light. And that has been a kind of a ceiling that we haven't been able to get through. And it puts a kind of a top speed limit on the maximum speed that a computer chip can be designed to process at. But utilizing this phenomenon, we now, we're on the verge of, and they're building them, computers which can compute at faster than the speed of an electron. And that's huge. That's huge. We have no known limit on the speed at which a computer will be able to compute based on this, because the speed of light, I think it's 186,000 miles per second, is, that compared to instantaneous is a huge difference. So that's why there's been a whole lot of research in this area, and it's been building for many decades. Schrodinger was somewhere in 1940, and physicists have been working on this and working at it and trying to, come up with different experiments and apparatus to illustrate it, and then ways of applying it based on the observed phenomena. And it's brought us all the way to today, to 2020, where they're building computer chips that are quantum computer chips. So I ask you, where is it going to go from there? What are the limits? And that's not even mentioning the fact that we have evidence that the human mind, the human consciousness, operates and exhibits quantum phenomena as well. That's also huge. So this is two huge things. All right, here he goes.
When there's no way for information to pass from one particle to the other, indicating which way to spin to obey the rules of entanglement. It's not surprising, then, that entanglement is at the core of quantum information science, a growing field studying how to use the laws of the strange quantum world in our macroscopic world. like in quantum cryptography, so spies can send secure messages to each other, or quantum computing for cracking secret codes. Everyday physics may start to look a bit more like the strange quantum world. Quantum teleportation may even progress so far that one day your cat will escape to a safer galaxy where there are no physicists and no boxes.
All right. It all sounds amazing. It all sounds like, man, I can't wrap my head around that. It's just, wow. But we have people, very, very intelligent, gifted, and diligent physicists who are showing this, demonstrating it over and over again. And they're beyond the level of demonstrating it. They're working on all the different ways that it can be applied. So there's a little intro to the discussion about this and why we discuss it and why it matters. And the only way that we can work with this is if we kind of keep it simple and just don't get into the calculus of it. The mathematicians, they put up walls of numbers and formulas and equations, and I'm not the greatest mathematician in the world, so I really can't follow what they do. But we can see the results of what they've done. What are you thinking, my friend? What are you thinking? I got a couple articles we can read too.
Yeah, I'm digging for some notes I had on the White House's quantum initiative. I think it'd be a good time to show that again. It's been 2 months or so, I think, since we've even brushed on that. And right. I think it's important to show it, number one, for the sheer amount of money that they're throwing at it. But number two, to maybe highlight and illustrate some of the laboratories that are involved, the national laboratories, and some of the partnerships that they indicate that they're forming with colleges, academics, as well as with
military,
commercial institutions.
Yep.
These are not the $2 billion initiative was for non-military purposes.
There's a huge amount of money that's been thrown at this. Huge, but there really should be a huge amount of money thrown at this because it's just really big.
This is the new internet. This will be the new internet.
Yeah.
The new internet will be a quantum internet, and 5G, the complex phased array systems with 5G are going to provide the wireless quantum connections of the future. And that's going to be the basic level connection. When we go to 6G and on, it's just going to get more and more complex. There's a lot more going on with 5G than just, what the cell phone companies are telling you can do with it. There's a lot more going on. So I'm going to dig for that real quick.
Yeah. While you're digging, take your time. I got something that I can read here, and it's kind of another look at it. So this is from sciencealert.com, and we can put the link out there for you. And this is just another way of explaining. I need this in simple form. I need it this way. I'm not a calculus genius. I'm not a master physicist. I'm just a regular person like all you folks out there. And I'll take a minute and just read some of the comments here. Hi, KLC. Good to see you out there. I see you got some comments there about the politics going on. We're kind of focused on this right now during this show. But Rocco to the rescue. I said, I don't know where this is coming from, but this quantum stuff makes me think that we might be capable of manifesting whatever we want the results to be. And that is, I agree with that. And it almost seems, if once again, if you review last week's episode, the quantum world is one in which all possibilities exist at the same time and all times exist at the same time. They are a state of reality that is like a fabric, a matrix, a canvas upon which we pluck certain eventualities from that fabric, and those become the reality. Once we identify that location on that fabric of quantum reality and bring it into our own consciousness, we have given it the measurement that was spoken of here. The measurement occurred. And at that point, that's when it becomes something that has transcended those extra dimensional parts of reality and come into our earthly dimension. So if that made any sense, Rocco, tell me if that made any sense, would you? If that makes any sense, that is exactly what physics would describe as the way that we might be able to manifest whatever we want the results to be. And it's within reason, because there are also multiple quantum entangled interactions between many of us and our individual consciousnesses, as well as our shared consciousness. And if you think about that, that's huge. We could talk about that a little bit later too. Anyway, for this little article, excuse me, from sciencealert.com, what is quantum entanglement? Okay, describes a relationship between particles and their fundamental properties that cannot have happened by chance. This could refer to states such as their position, their momentum, speed, or polarization. Polarization being related to their spin. One might be clockwise, one might be the other clockwise. So, okay. Think of a pair of gloves. If you found a right glove alone in your drawer, you can be certain that the missing glove would fit your left hand. Beautiful example, isn't it? Beautiful. Gloves come in pairs, shoes come in pairs. So you find one and you know that the missing one is the opposite one. You know it. You didn't see the left-handed glove yet, but you know that it's out there somewhere because you have the right-hand glove in your hand. That's just such a simple, beautiful example. So continuing, the two gloves could be described as being entangled, as knowing something about one tells you something very important about the other one that is not a random feature. In this fashion, this concept isn't strange at all. The concept poses a problem for quantum mechanics. Now, let's see how far this goes, because it will possibly start to get a little bit more complex. But wouldn't you agree that it's just so simple? That at least that part of quantum physics is intuitive. We understand it because we can relate to it. Our job here in discussing this, we're not just trying to, smoke everybody's brains out. We're trying to really bring this to a general understanding for all folks. By the way, welcome, Old Stock White Canadian. He writes, it is the basis of physics. Nothing is gained, nothing is lost to each force. An equal force reacts. Yes, he's speaking about there being, if you've got two entangled electrons and one of them is rotating clockwise, you know the other entangled electron is rotating counterclockwise. Yes. And it also extrapolates from that for every action, there is an equal and opposite reaction. And then goes on. Wow, Old Stock White Canadian, that's a long name. I like it. Would be that perhaps we might consider that this has parallels at the conscious level, as you just said. Responsibility as to how we think and perhaps how we interact with others. I would pose a question to you out there, Old Stock White Canadian, that when you indicate that there's a responsibility that we have, and the power of our thought, the power of the choices that we make and how those may interact with other people could be a really big thing. And I think that we're drawn in this current very busy, very process-oriented, logistical world that we live in of very little time to get a whole lot of things done. I don't think we get to take enough time to consider the ramifications of our actions and even our thoughts enough. But I believe that we all interact with each other a whole lot more than we think. Anyway, I could blabber on for hours. Let me just read a little bit more of this. So, quantum entanglement and reality. Physicists Niels Bohr and Werner Heisenberg argued that an object state only truly existed once it became associated with a measurement. In other words, somebody needed to observe it experimentally. Until then, its nature was a mere possibility. Okay, I'm going to go back to the two gloves. Let's say I have knowledge about my gloves, and I know that one of my gloves is missing, but I don't know which glove is missing. I know that gloves come in pairs, and I know, say somebody told me, or I got some outside information that said, hey, Indy, one of your gloves is missing. Well, I don't know which one's missing yet. But if I find one of them, then I know which one is missing. Anyway, they go on. Okay, two other physicists, Albert Einstein and Erwin Schrödinger, the infamous cat example guy, said this was as preposterous as saying that a cat inside a box is neither alive nor dead until you look at it. Okay, so they're antagonizing the theory of Niels Bohr and Werner Heisenberg. But as you can see, this was many, many decades ago. And physicists have been ruminating about this for years, and they've gotten a whole lot closer to the truth and the reality of it since then. Finally, two physicists, Boris Podolsky and Nathan Rosen, collaborated with Einstein to come up with a thought experiment where two objects interact in some way. By measuring one of them, we might be able to work out some of its partner details without needing to measure the partner directly, thanks to its entangled history. Okay. And then the last little piece I'll read from this before I either pass it back over to you, TMC, or I can go to the other video too, which is kind of cool, is this. Spooky action at a distance. Spooky, it's not, that throws a lot of people off. It's just incongruous action. It's just non-intuitive interaction about these things that we can prove happens. That's all it is. All it is something that you just say, how the heck did that happen? And there it is. And you know what? Let's run the experiment again. And whoop, lo and behold, it did the same thing again. I measured particle A, and that tells me what particle B is doing. And it goes on. And in the true spirit of engineering, they take a simple theory and then they start building a structure of design and devices upon it. And there we go. Today's quantum computers. Going to be applied to all sorts of things, such as blockchain technology. It's going to be utilized in enhancing the power of artificial intelligence. Danger, Will Robinson. We need to make sure that we know where that power of artificial intelligence is going. Could be scary, could be great. I'm just saying. Anyway, spooky action at a distance. In response to this dilemma, Niels Bohr suggested that the state of both objects simply became real at the same time, as if they instantly swapped details on this experimental intrusion that occurred across a distance. Okay, so he's saying they instantly swapped details. In other words, they communicated with each other, and we don't know how they communicate with each other. We don't know that. We don't know. All that we know is that they do it. We don't know how they do it. Hence, somebody along the line termed the idea, it was Albert Einstein, termed the idea as spooky action. All right, well, come up with any descriptor that you want for it. Decades later, Niels Bohr's ideas stand strong, and the strange nature of quantum entanglement is a solid part of modern physics, and you can take that to the bank. And that gets to what I'm sure TMC's probably got it almost ready to present now about.
Yeah, I want to stop you real quick. That statement or the sentence written about Einstein is that he dismissed the idea as the spooky action, meaning that he dismissed this idea of it not being quantifiable, claiming on multiple occasions that God does not play dice. So what he's saying is you remember the statement that the yogi made, or the quote, so to speak, from Einstein, where he indicated that mysticism was just simply something in science that has yet to be discovered, but that in and of itself was very beautiful, and by that nature, it's mystic.
Yes,
and that's all mysticism is really just misunderstood or undiscovered science.
Exactly.
To me, that's what I that's what I see him saying here. Einstein dismissing this idea of spooky action at distance, indicating that, he said, quote, God does not play dice.
But what gets me is his last phrase, that God does not play dice. Well, I would tend to agree with that. God does not play dice. But it almost sounds as if Einstein is dismissing the ultimate and completely overarching power over all things in the universe that God, if you wish to use that term, or a creator of all of it, would have. No, the creator of everything that we see, from the submicroscopic and subatomic all the way out to cosmological distances of space and time, would not likely be playing dice. It would likely be something that is an ingeniously integrated firmament of everything from all of those scales, all the way from the tiny to the very, very large. And it's not likely at all that it's by chance. If you look at the structure of life and DNA, and you look at the order and organization in the universe that we've been able to observe, this isn't playing dice. We just don't happen to have it figured out yet. So I don't know why he really brought God into it in that context.
I think it has to do with maybe the time in which it was said, and maybe he was God-fearing, who knows?
But why dismiss it? Why? It's almost as if Einstein chose to just oversimplify it and brush it off.
Why dismiss?
I
don't think he's brushing it off. I think what he's saying is that those that are dismissing it and saying, "Oh, it's spooky act at a distance," we can understand the observation, but we don't know why,
right?
And therefore, we'll call it chance. To some extent, there was this debate over, is it chance? And it's just, we're able to predict what the universe is doing as chance. We're able to predict that. Yep. And to some extent, I think that's where he was coming from. Einstein saying, no, it's back to this root of cause and effect. If there is causality, even if we don't understand what the cause and effect is, there is some standard mechanism that's at work.
Yeah. You know what? On second reading, I think I'm agreeing with you now. He wasn't really dismissed. He was he knew
it's
there was more.
From what you're saying.
Right.
Yes.
He knew there was more.
He's dismissing this idea that it's random.
Yep. Exactly. And in fact, he might even take issue with the idea of using the phrase spooky.
Right.
Because I don't think it's really spooky at all. We haven't figured it out yet, but we're getting closer. Anyway, there we go. It's a solid part of modern physics, and physics. See, this is it. This whole spooky thing. I'm just going to say, forget about the spooky. Physics really is something that we have not completely figured out yet. That's all. I'm rephrasing this last sentence right here, and I'm saying we just need to keep working at it.
Well, I think spooky's okay. I think if we to some extent try to define it, and really when you think of spooky is like scary. And so when I see that, it's more or less a fear or concern or a lack of confidence about something that is unknown.
We have there's meaning that comes along with words when they're used, and they tend to influence our mood and our emotions. And I think it would be an error for us to take that word for what might be a dictionary meaning. And for, the folks out in the chat, I don't want them to get spooked out. I'm not spooked.
I think it's ironic that you're talking about scientists who deal in ultimatums and infinitums, right? Physicists and astrophysicists and everything, and they're throwing around a word like spooky, and I mean it's a little antithetical to their profession,
Yep.
Yeah.
Yep. I think we all understand what
the link.
I'm glad we talked about that for a few minutes. Further comments are needed from the group out in the chat. We got to really come up with a good group thought of what we're going to call what's not so spooky, just what's kind of a mystery. All right, what do you got?
So I'm going to breeze through these quickly, and just to highlight where we're going. White House announces $1 billion investment for AI and quantum computing hubs, August 26, 2020.
That's just for the hubs.
Right.
That's just for the computing hubs. That's not for the overall research effort, the thrust on the part of all of the institutions, plus the government and that's probably encompasses the military, but it's a lot of money already.
So here it is. Last year, the Trump administration rolled out executive order on AI, declaring its intention to bolster U.S. dominance in the field. But the order didn't address much in the way of funding. This February, the Trump administration called on more than $2 billion to be invested in non-defense AI and quantum research. So,
and, two things. I don't think that President Trump is a big fan of spooky things either. I think, he says, okay, we don't want China to get the lead on this. This is important stuff, and we're going to throw some work and research and talent and money at it and stay ahead. And I like it.
University involvement, National Science Foundation, $20 million apiece to these schools. University of Colorado, University of Texas, Oklahoma, MIT, UC Davis, University of Illinois, ×2. Department of Energy, linked centers focused on quantum information science. Quantum information science.
Notice DARPA didn't show up on the list yet.
Well, I bet you search DARPA you search DARPA and quantum, and I bet you're going to find plenty. It says here, the Department of Energy quantum centers will be established. They're establishing quantum centers at these national laboratories: Brookhaven National Lab, Argonne National Lab, Fermi National Lab, Lawrence Berkeley, Oak Ridge National Labs. And these are major infrastructure investments to the university as well as to the national laboratories that develop technologies that ultimately trickle down to us. Most of what's in your cell phone comes from groups like this.
Yep.
For example, Microsoft and Intel, among other tech industry partners, are committing staff and equipment to help establish the new institute. So here's this blending of big tech, if you will, and hardware manufacturers, just call it big tech, merging or partnering with the Department of Energy and also with these schools to develop quantum computing and AI endeavors. That's just one article.
Yep.
And this one's kind of a repeat. So I'll just show you. This is Wall Street Journal. You can search this stuff. A quantum AI initiative. White House announces $1 billion to create AI and quantum institutes. And you've got another one here. This is from the White House itself. whitehouse.gov. Trump admin is taking strong action to ensure American leadership in industries of the future: AI, quantum information science, 5G, and other key emerging technologies that will shape our economy and our security for years to come. These are all related.
Yeah. Economy and security.
Science, artificial intelligence, and 5G. What's that?
Economy and security, both. Yes, it really is a place where we need to not lose. Well, we certainly don't want to fall behind.
Yeah, if you don't have a good economy, you don't have a good military. They go hand in hand. So without a good economy, your military is not effective. Period.
And we're not hearing much about, and I'm not trying to vilify China, although I'm not a real big fan of them these days, but don't think for a minute that research labs somewhere under the direction of the CCP are also working on this as well. You know they are. We're not hearing about it, but they are.
Everybody is.
Yep.
So this patent is from Verizon from many, many years ago, and this is from 2006 originally. Verizon Patent and Licensing.
06.
A space-based satellite device obtains one or more encryption key symbols. A satellite device transmits one or more encryption key symbols to multiple nodes of a land-based network using quantum cryptography. And what I want to show you here,
look at that,
is that they're able to send and receive key management systems, right? Keys, quantum keys via radio frequency links, satellites, right?
Yep.
And there's 23 references to RF in here. So you have radio frequency transmitters and receivers. Here in this case, it's a transceiver. There's another search term that's linked here. And without going too deep into this patent, they literally talk about the physical layer of sending electromagnetic waves and using the physical transmission of electromagnetic waves to create quantum entanglement or to quantum encryption.
Does that create the entanglement, or is the entanglement created and then they transmit RF? And what happens is the time is saved at both ends in terms of the processing. And the level of encryption of that is huge, because unless some third party or a man in the middle has a way of knowing what the state of the quantum value was at the transmitting end, they can never know for certain what the state is when it's deciphered, when it's decrypted at the receiving end.
It's sending quantum particles. So it's able to use a transmitter. It says in this paragraph right here, quantum modulator. Quantum modulator may modulate a state of each quantum particle emitted by a quantum source to encode each quantum particle with an encryption key symbol value. In one implementation, a quantum modulator may modulate the phase or polarization, just as you read a minute ago, and or the energy of the emitted photons. So the energy is directly related to the frequency, and the phase and the polarization has to do with the timing with which the energy is transmitted, and the polarization has to do also with how it's actually generated from a transmitter. So a quantum modulator can include this interferometer, blah, blah, blah. A quantum beam directional control may include the control circuitry associated. So all of this hardware that's built in behind the transmitter. Think about what's being built onto satellites.
Yep, and that's where those chips that they've designed that spit out quantum entangled particles come in.
Yes. And so what it says here is that the quantum beam directional control may include circuitry for directing a beam of quantum particles emitted from a quantum source towards one or more nodes. This could be inside a fiber optic cable, or it can be in open space, and I'll get to that in a minute. Directional control may thus permit satellite to aim its beam of quantum particles towards selected nodes of a land network. So we're talking about sending beams of energy from space, from a satellite down to a node.
One or more nodes.
You don't have a cable connecting a satellite to the ground. So they're talking about sending quantum encryption language or information through free space. And they actually use that term here. In one implementation, a satellite may include multiple free space quantum transmitters, each being capable of being independently directed. So you're talking about phased array to provide a beam of quantum particles to different ones of nodes. So to many different nodes. Free space quantum transmitter may distribute encryption key symbols to one or more LAN network nodes through the, looks like N, it's just a reference to a diagram in a free space link. So that's all I'm going to read from this patent. But what I want to illustrate, or I guess drive the point home here, is that this whole thing about 5G and this whole about radio links, we're moving past fiber optic cables, sending photons. What we understand is photons. When we think photon, we think light. But radio frequency waves, millimeter waves, microwaves, X-rays, gamma rays, infrared, and light, they're all on the same spectrum. They're the electromagnetic spectrum. They're all transmitting or receiving photons. Those are different energy states of photons. So if you go up in energy, if a photon goes up in energy, then you move higher up on the electromagnetic spectrum. X-rays and gamma rays have way more energy per photon than a radio wave, but it's still a photon.
Right.
And so when we talk about particle entanglement and entangling photons so that you have quantum entanglement with photons, this can be done with wireless energy transmitted through free space. And that's what it
really means, if I may,
is that we're here.
If I may, what it really means is that if you run it at higher frequency, then you can send more quantum entangled particles in the same amount of time, because it's just a higher frequency.
Yes,
the
yes
same
and no.
principle applies, but you can send more data faster.
It's perhaps there are limitations with that. Obstructions become an issue, and directionality becomes an issue. So the higher frequencies, you're able to point them and aim them better than the lower frequencies, but the lower frequencies transmit through debris. And when you think about a satellite transmitting energy from space down to Earth, there is a cost benefit to using higher and higher frequencies, being that you have to go through moisture and you have to go through 10 feet of dirt. I think it is. There's a large amount of dirt when you think about the atmosphere and how much space is in between the outer atmosphere all the way down to the ground,
the little
and how
dust
much
particles.
You got it. And so all of those things affect the photons. They bounce into those things and they reflect and refract and absorb and all of that.
Right.
And that impacts quantum entanglement. If there's too much interference, then it's deemed as being a compromised link, and the information is ultimately corrupted, which is why they get the encryption security the way they do with quantum encryption. You cannot intercept, so they say, you cannot intercept a quantum encrypted communication because the interception itself corrupts the data because the observation point has changed. This goes back to the Schrodinger thing.
But
you
know what else they could do? They could also send a duplicate of the information at multiple different frequencies, and because they might not know what it might encounter in the directional beam, and whichever one gets through, whichever ones get through are the ones that they get the successful transmission. They could do that too.
Yeah, I'm sure there are quality of service redundancies, if you will, put into place to balance things like debris in the atmosphere corrupting your data. I'm sure that's there, but there's a cost benefit trade-off there, because if you have like a Navy ship that's angling directed energy up into the sky and scanning for other directed energy coming down from space and trying to intercept it, that's also interrupting or interacting with the photons that you're trying to transmit as a quantum encrypted message, because you're having directed energy then cross over and creating wave interference that then changes the characteristics of those. Right. So there, like I said, there's a cost benefit there too. Yeah. So it's super complicated, but it's not when we just.
It isn't because computer technology and networking engineers are already familiar with, okay, I got to send this data and, it's either going to be over copper or fiber. If it's fiber, I got to deal with this, and this is the QoS that I got to the QoS protocol that I got to see what's going to work. Or maybe in this case, all I got is copper. All I have is a twisted pair of copper wires, old school stuff. So they're already familiar with with assessing the parameters of the success of a transmission. It's just different stuff. You know what I mean? It's not a new science for these people.
No, it's a different. What it is, it's a different physical layer that provides interesting characteristics and different benefits.
Yep.
If you can give someone or something complete and total anonymity with a quantum encryption, then there's a huge benefit to that.
Which is getting back to the heart of the thing. We kind of digress a little bit when we talk about, the beam running into pollen or dust, all that
dirt
stuff.
Or moisture or whatever. Yeah.
But the principle of what we're talking about is still, that's the main thread that we're on. By the way, hi Powder, good to see you out there, and everybody else too.
A couple more, and then I'll throw it back to you for the video. Energy.gov, and this just kind of going through these relatively quickly. We stopped and spent some time on the free space transmission for quantum encryption keys, because that's a critical.
The biggest takeaway from that was actually very important, because everybody should know that this is work that is being actively pursued for the purpose of refining it and making it work better and better. And they're doing it. It's already here. They're not telling you about it, but huge budgets and huge interest in it for all the purposes that we talked about. Super secure transmissions. It feeds into keeping crypto transactions secure, as well as any other vitally important secrecy. It's a level of encryption that we've never had before.
If you can establish a quantum wireless network, then you don't need to have cables and fiber optics and copper. You don't need to have that going anywhere. All that will, from a business case, will go away. Whether or not it's healthy or unhealthy is entirely independent from the efficiency and the effectiveness of what it is that's being developed. And so there's different ways to look at this problem, and the health concerns are just one perspective to view. Here's something from Congress.gov, the National Quantum Initiative Act. There's an actual bill for it, or an initiative, I should say.
I'm trying to. It's small on my screen. What's the date on that? Let's see here.
December 21st, 2018.
Okay.
Yeah, 12/21, buddy.
Yeah. Whoa.
Yeah. So a year after the 12/21/2017 executive order, and 12/21 just seems to keep popping up. Anyway, coincidence?
Shortest day of the year.
What's that?
Yeah. Shortest day of the year.
Right.
Also happens to be when we cross the galactic plane, but we can talk about that later.
Yeah, if we have time.
Yep.
This was February 11, 2019. This is the EO on maintaining American leadership in artificial intelligence that was referenced in one of the articles earlier.
Right.
So it's out here for your public consumption. I mean, all this stuff is public information. If you want to go look this up and read it, it's all there. And what else is in here that's interesting? You talked about DARPA earlier, so we're going here, buddy.
Yep. Let's do it.
So this is an archive piece, DARPA, and this was back in
February 2019.
2003.
Oh, 03. Excuse me. Yep.
Yeah.
Wow.
Yeah. So it talks about this is a proposal, a solicitation for a proposal, technical areas of interest, right? New materials, material concepts, material processing, engineered materials, biomaterials, biomimetic materials, fracture phenomena, femtosecond laser diodes, optical amplifiers, ferroelectric, magnetic, etc. There's a reason for me to say all
by the way,
this.
a femtosecond laser diode is an extremely ultra-fast switching diode.
It's the order of magnitude higher than or lower, faster than a
nanosecond. Yep, right.
Right. So femto is faster than nano.
Yep.
Quantum, so materials and concepts for power generation, energy storage at all scales, materials and structures for quantum information processing back in 2003. 20 years ago, basically. Material structures for quantum information processing, materials and structures for spin, transport, and control. When we're talking about entanglement, having an upspin or a downspin, and then having a known relationship. So they were already into all that.
Yep.
Multifunctional structure and function materials, non-destructive evaluation, property, life prediction, related technologies, blah, 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 blah. Advanced math. DoD specific areas include computational geometry and topology, dimensionality reduction, electromagnetic modeling and simulation, fast scalable scientific computation, quantum information science when they're talking about math, sensor management, signal and imaging processing, virtual materials development, processing and evaluation, and they get into biowarfare and everything else.
Biowarfare. Wonderful. Yeah. By the way, Light Switch, how you doing? Good to see you.
Yeah. Well, here's an interesting fact. They can create multi-photon ionization with femtosecond laser pulses. Multi-photon ionization. And what that means is that they can use non-ionizing radiation, transmit multiple photons of non-ionizing radiation, and create an ionization impact. using non-ionizing
Even-
radiation, pulsing
Even
it at
starting with
femtosecond.
non-ionizing radiation to
That's right.
begin with.
And they're pulsing it fast enough in the femtosecond range to actually ionize materials.
And that is due to something else that we discussed. Don't ask me how many episodes it was, but that's due to the constructive and destructive interference overlap between those multiple photons that they're producing. They'll reach a point at which there is an interference pattern set up so that there is a different frequency from the one that they were originally transmitted at.
Yeah, and they can actually generate. They can also generate plasmas with femtosecond lasers. And lasers are just photons. It's just what part of the spectrum are you using? There's lots of creepy stuff they can do. Cool stuff. What else is in here? There's
And to demystify that, anybody that's got a musical instrument, you play one string on a guitar and play another one, but then you play both of them together and you hear an interaction between the two. That's all that we mean by an interference pattern. That happens to be with audio. They're doing exactly the same thing with these high-speed switching laser diodes, and it creates a different frequency from the one that came out of either one of the diodes. And they could even do it all with one diode too, by the way, but that's beside the point.
This is an interesting article, an introduction to quantum game theory.
Game theory?
Quantum game theory. They use this for economics.
Oh.
Mm-hmm. This essay gives a self-contained introduction to quantum game theory and is primarily oriented to economists with little or no acquaintance with quantum mechanics. So economists who know nothing about quantum mechanics. It assumes little more than basic knowledge of vector algebra, so distance and speed, or direction and speed, vector
direction
algebra.
and speed, right.
Quantum mechanical notation and results are introduced as needed. It also shows that some fundamental problems of quantum mechanics can be formulated as games. So game theory using quantum information.
Man, is that fascinating or what?
Yeah, it's an interesting read, but it's difficult to understand. It's one of those things you got to read a few times. And then this whole thing about QNext, and this is from Argonne Labs, and this is
notice the common thread that comes up in everything that we're surveying is quantum, quantum, quantum. Mm-hmm. And there's no question about the size of the budgets involved and the number of people who are focusing on this.
QNext. So this is one of the major pushes through the national laboratories. This is one of them. There's a few. But this QNext does a really good job kind of explaining quantum information science and why this push, or some of the goals, I guess, with this push.
That third paragraph down might be a good one. Well, yeah, go whichever one you want, but I definitely don't want to skip the third paragraph down.
Yeah, so QNext is a national quantum information science research center supported by the Department of Energy. It's led by Argonne National Labs, and it combines expertise and resources of nearly 100 world-class researchers from 3 national labs, 10 universities, and 10 leading U.S. technology companies. So here's this corporate, public, private, university, national laboratory partnership, this fusion with quantum information science, have profound impacts on long-term U.S. economic security and competitiveness by enabling unhackable communication channels and by creating quantum materials, sensors, and simulators that outperform any of our current systems. So
unhackable communications, TMC.
And simulators to outperform any of our current systems. So think about running R&D anything. I want R&D in this particular field and fill in the blank. Medicine, material science.
Better simulations, better virtualization.
What supercomputers do now, I forgot the analogy. It was a million years or 100,000 years, something like that. They could do it in a few seconds. A quantum computer can compute as much information as a supercomputer. And we're talking thousands and thousands, if not hundreds of thousands, if not millions. I don't remember. And then that's with the supercomputer doing the computation. Classical computer, even though it's a supercomputer, it's a classical computer using transistors.
And it's the size of a building.
Right. Rather than a quantum computer.
Power plant to run it.
Mm-hmm. Rather than a quantum computer doing the very same thing in a matter of seconds. So it's this idea of inputting information, data sets, and running simulations and coming up with likely outcomes, probabilistic probabilistic outcomes. And that's what the quantum computer is very, very good at.
Hang on. Let's dwell on that for a second, because it's easy for people to brush off the idea of simulations, right? Simulations. Okay. But imagine a simulation that is more and more of an accurate representation of the reality, and then dial it in further. Now, keep in mind the scale difference between quantum computers and classical computers, okay? We're talking about orders of magnitude of much more computations per second, and we're talking about magnitudes of order of being able to process or simulate so that your representation of the reality becomes closer and closer to the actual, until you reach the point that that simulation is so precise, the precision of it would have the capability of being down to such a level of granularity that hardly anybody under any condition would ever be able to tell the difference between the simulation and the real thing. All done with the power of quantum computing. And
very, very quickly. And then take it a step further. When changes are input, you would be able to scale the outcomes of those changes very, very quickly. So
immediate adaptation.
It's not a big deal. Yep. Very good way to concisely to quantify that. Yes, that's exactly right. Very efficient, immediate adaptation to.
Because how fast is quantum phenomena? It's so fast we can't even measure how long it takes. For all intents and purposes with our measurement equipment, quantum phenomena are instantaneous. So the rate of adaptation, instantaneous. My gosh, the power of that.
Yeah, and that's not even talking about some of the people, the quantum scientists are saying that when they run these quantum computers, the amount of input they put in, they actually get like a 10% surplus energy state back, information state back.
Which to me would imply that what's going on in that quantum processor is actually tapping into something that's extra dimensional from what the scientists didn't even know that they put.
That's right. They're saying that we're pulling in. That's what they're saying, is that the easiest way to say that in a layman's term is that we're pulling information from another dimension into ours, where we get our information back or whatever we're trying to do with it, but we get extra information. We're getting extra information.
When you get more than you put in, where did it come from? It came from someplace else.
That's right. And
that's so significant. Yeah. That's almost an inferential proof of what we've been talking about for the last couple of weeks, which is the existence of dimensions beyond our normal earthly perception.
I'm going to go out on a limb.
Almost a proof of it.
I'm going to go out on a limb and use a word here and say that's spooky.
Oh, jeez.
Was that corny?
It's spookier than putting a cat and a stick of dynamite in the same box. Anyway,
If we weren't on air, Indy, I would say that sounds like fun, but we're on air, so I'm not going to say.
No, don't do it. Don't do it. Okay.
I'm a dog lover, man. I'm not a fan of cats, but
I like them.
Anyway.
Quantum mechanics is one of the most important. I'll get one of the most.
So down here is what you want, right?
Yep.
Yeah, very good. Go ahead.
All right. Quantum mechanics is one of the most important achievements of modern science and has enabled the development of revolutionary technologies such as the transistors that power electronics and computers, the ultrasensitive detectors used in medical imaging, and atomic clocks used in GPS satellites. Quantum information science uses the principles of quantum mechanics to open up completely new ways to collect and process information. This will allow us to overcome many of the fundamental limitations, which we spoke about earlier, of our traditional sensing, communication, and computing networks, which are two of our focus areas in Q next. The implications of quantum information science on our economy and our nation could be, I'll go out on a limb and say, will be transformational. They will be, and they are being that now in their primordial state. We are he went and said that. We are already seeing significant commercial interest arising from the promise of quantum computing systems to provide perfectly secure communications, novel solutions to highly complex optimization problems in finance, healthcare, and I'm going to add economics too, more accurate measurements of physical phenomena and far more realistic simulations of the real world. And what's everybody interested in these days? Virtual reality.
So this part's important. We were talking about quantum computers and trying to understand. Yeah, like I said, this is a great article.
Jeez. Yep.
So how do quantum computing and communication differ from traditional computing and communications? A prime example is in quantum communications, a QNext focus area. One of the non-intuitive principles of quantum mechanics is that if you try to spy on a quantum encrypted communication, the information in the communication is corrupted and becomes unreadable. Quantum communication can therefore be fundamentally secure in a way that no traditional communication can. Quantum-based computers exploit these phenomena as well for some problems, particularly in areas such as cryptanalysis, simulations of the physical world, or optimization of complex problems. Things like figuring out complex gene therapy for cancer would be a complex problem that needs optimization, running many scenarios to pick the right DNA, RNA stack so that when it's introduced into the body, it self-assembles and releases medication at a tumor. Complex problem in medicine that quantum computing would be able to model.
Repeat that again. Your voice blipped out, dropped out for a minute. That last thing you just said.
So what I was getting at is an example of a complex problem would be something like developing cancer medication that's targeted gene therapy, where they needed to run simulations of how proteins are made and folded, or how the DNA folds and wraps around medicine, for example, and then how it's triggered and released on site at a tumor site, all so that it doesn't destroy the host. Right. So a complex problem would be treating an aggressive form of cancer with DNA-based therapeutics. Not that it's going in and changing your DNA, although it could.
That could. That's different. Yep.
Using DNA as a structure, as a suitcase, if you will, to carry medicine into the body, deliver it where it needs to go, and then unzip and open the suitcase and deliver the medicine directly at the tumor site rather than injecting chemotherapy into your veins.
Right. So, biomolecules are very complex. DNA strands, very, very complex.
So what they're getting at here is a quantum-based computer being very good at cryptanalysis, like we're talking about, unhackable communications, simulations of the physical world, being able to predict likely outcomes based on the amount of data that's coming in. Think Internet of Things, capturing all the data from all the sensors and all the phones and everything, and then figuring out what the likely prediction of future events are, being able to predict the future and be able to steer the future. And then this last piece, or optimization of complex problems. So things like advanced therapies, advanced medicines, targeted medicines, genome-specific, person-specific medicines. If you were to deploy quantum computers to a local community, you would be able to very easily optimize complex problems person to person to person. You go in, you have an illness, they draw your blood, they scan you, and they run your information through a quantum computer, and boom, you get a cure that's targeted for you.
Real fast. Right. The results are real fast, and you got to realize every individual is different. That we're all put together just a little bit differently. So it's going to be, if it's going to have full effectiveness, it's got to be accurate. And that's what we're talking about here, is more accuracy, better simulations, super precise simulations.
So it says quantum-based computers will perform calculations much more efficiently and accurately than traditional computers. The QNext developments in quantum sensing will have several applications in quantum computing, from the testing of nano-electronic circuits to serving as qubits, quantum bits, the basic unit of quantum information. So when you get into the nano size, I saw a comment in chat about quantum is on Bill Gates something or other. Well, yes, that's true. Because when you look at what quantum dots are and other forms of nano electronics, you can look up Charles Lieber, the guy who was arrested, working at the Wuhan University, part of the 1,000 Talents program, taken into custody and is now, I'm assuming, waiting trial. Things like espionage, or selling of state secrets, because this guy did work for DARPA and the Air Force on things like putting nanoelectronics inside neural tissue, inside the brain, to create brain-computer interfaces for groups like the Air Force.
Nano, and small and fast.
Nanoelectronics.
And very, very fast. That's the thing.
Well, the thing about nano is when you're dealing with electronics or conductive materials or anything at the nano scale, they function in the realm of quantum physics. So this is where the quantum computing and the quantum information science comes into play at the nano scale. So a piece of metal in the macro scale, what we would see like a chunk of metal on the table, right? Right. Does different things when it's a piece of nano metal. It doesn't respond the same way. Things that are magnetic are not at the nanoscale, for example. I'm not saying all, but some, and vice versa. Polymers, for example, that don't conduct electricity and have no magnetic properties, something that's the size that you'd be able to see or pick up on your table, at the nanoscale, all of a sudden they emit they exhibit, dielectric properties, magnetic properties,
and electrical properties,
conductive properties. Again, this is not all polymers.
Because it's getting down to their atomic level. And at the atomic level, everything is about charge. Positive
quantum
and negative
phenomena
charge and spin.
Occur.
Yep. Just acknowledging the chat out there. Light switch, access to different intelligences, sure thing. But and then indicating like the thought about alien information. Light switch, I would submit that what we might think of as alien information might not be at that quantum level in the fabric of quantum reality, might not be so far removed from what we would be able to perceive or sense somehow. We just aren't fully opened up to it. And so that's one thing. And then Old Stock White Canadian just had a comment to the side there, which was, say again?
I said he nailed it. That's exactly what I think has already happened personally. Go ahead, read it.
Yeah. And so anyway, good comments. We're seeing them all, and we're paying attention to you guys out there.
He said, imagine the spying now embedded within the biology of an individual, even without their knowledge. This goes into this idea of smart dust, or if you listen to Julian Assange, evil dust. That's what he called it. But he was talking about smart dust. And what I was talking about earlier with Dr. Lieber and his nano bioelectronics and cell scaffolding and nano transistors, all of these are families or within the same general family of nanoelectronics that can basically be used in biologicals such as humans.
Yep.
And that's
by the way, Old Stock White Canadian is a lady, a very nice lady. We've been working with her quite a bit, so she's a lady. Just want to throw that in there.
Yeah, thanks. if I said male, I apologize. So, do we want to keep going with this thing, or
let's come back? Hold on that next paragraph. We have another guy who's gonna smoke our brains a little bit more on a little bit more about quantum physics, and we're not going to play a whole lot of it because he does get a little technical after a while. But at least he starts off simple, and I got it sort of ready to go here right now, and that's coming up right here. Okay. All right. And he's got 15 minutes worth, and we're not going to have to go through all of it. We don't even have time to go through all of it right now. This is a multi episode discussion that we're having, and we're gonna tie this into a lot of things that we've been talking about. How long have we been doing this, TMC? Like more than a year now. It's all gonna really start to tie together.
Since we started with America Live, it's been a few months, but prior to that, we're pushing
a lot.
What month is it now? It's November. Yeah, we're literally almost at a year.
Yep. So I think that we're going to try to tie it all together, and we encourage people to watch old episodes, and also really would want to encourage you to go and check out TMC's his library of information. It's over at https:// You can tell them the rest, TMC. humaninternet.org.
Yeah, it's humaninternet.org, because that's really my focus, is trying to understand methods and mechanisms, which there are many, different ways to put the human onto the internet, or to merge the human onto the internet, and do it in ways that the stuff I'm looking at is through publicly available information, listing public patents and science-based information, white paper information on
Factual stuff.
technologies that exist in things like cell phones, tablets, televisions. Yeah, real stuff. It's not, I mean, you can look up all over YouTube about targeted individual information, and the government's listening to your thoughts and all that. You can see all the bombastic, flamboyant, well choreographed, well produced information, and people would call that fear porn or conspiracy, and that's fine. Whatever. I get all that. My approach is a lot drier than that, but it's very much data oriented. I list patents, I list white papers, and I list YouTube videos where experts in their field literally talk about the future of the human species and its relationship or its fusion with the internet and with artificial intelligence. So that's at humaninternet.org. It is a work in progress. It is not perfect, and I'm glad it's not perfect, because it's made by one person with the input of my sphere of influence, Indy being one of my close sphere of influence individuals.
And it's developing.
It is raw and it's unfiltered.
It evolves. It has to develop.
Yeah.
At some point, like at which point it was done, then it would no longer be alive, vibrant, or dynamic anymore. So of course it's got to evolve. And I wanted to offer you another thought, which is the factual information that you have there. When we combine that together with a little bit of discussion, a little bit of sometimes speculation, but when you tie that together with the facts, then we're actually better off when we extrapolate a little bit from what we see as the known concrete devices and developments and patents, and you've even followed patents that have then gone on to a state of further engineering refinement to the point that they end up hitting the shelves for consumer electronics. All right, so it's all based on fact. And then when we speculate on top of that, rather than that being crazy imagination, that's more like the frosting on the cake of what the science and the facts and the research and the devices that have been built that we started the whole discussion on. So this is really the best way to do it, is a combination of both. And I might add, science fiction writers from years ago have been shockingly accurate in what they have predicted would come to pass in today's reality. I just wanted to throw that in. Shockingly accurate. All right, so credit where credit is due. This is from Fermilab. This is a YouTube video, and it is about quantum entanglement, and we're going to give it a go. And I think I got it all checked off and set up, ready to go here. And we'll go a little ways into it, and then we'll stop.
But it got me to thinking, and I realized that I should have told her about a thing called quantum entanglement. It still blows my mind. Let's see if you agree with me. Broadly speaking, quantum mechanics is a physics theory that describes the behavior of atoms and even smaller particles. But quantum entanglement allows for weird quantum behaviors to be seen on sizes as big as people or even larger. So just what is quantum entanglement? In an earlier video, I talked about how the behavior of a subatomic particle, like a photon or an electron, is described by what is called a wave function. Brushing over many details, the wave function governs the probability that you will find the particle in a particular configuration. Before you make a measurement, you can't know, even in principle, what configuration the particle is in. To give a concrete example of what I mean by the word configuration, let's use the direction of the spin of a particle. Now, there is a quantum weirdness in that when you measure the direction of the spin of a particle, you first have to pick a direction, and then the outcome will always be either in the direction you picked or exactly opposite. It can't be anywhere in between. So, if you picked a measurement direction to be horizontal, the measurement of the spin direction could be left or right. It couldn't be up or down, forward or back, or any direction except.
You see how that ties into that example of the left and the right hand glove. If you found the right glove, you know the missing one's the left-hand glove. It's not going to be half left. It's not going to be a four-fingered glove or, whatever. It's not going to be a mitten. It's going to be a glove. Anyway, that's all he's doing with that. This is review, but it might be good just to have multiple ways of expressing the same thing so that everybody can get this locked into their minds about what entanglement is and quantum physics is. This is real stuff.
For right or left. On the other hand, if you decided to measure in the vertical direction, the only outcomes of your measurement would be up and down. Left and right would be forbidden.
So I know I'm stopping him a lot, but I think that we can all relate to the fact that we know that computers operate in a binary fashion at their most basic machine level. It's either ones or zeros. Now that lends itself very, very well to the on-off state of up-down spin. If it's spinning up, it's going to be up. If it's down, it's the exact opposite. The exact opposite of either an on state or an off state in a computer. So this entanglement of particles and entanglement integrated circuits that produce entangled electrons lends itself perfectly to to quantum computing. Perfectly. It couldn't be better. There's no in between. Computers are either 1 or 0. Anyway, there he goes. Here he goes.
It's certainly counterintuitive, but it's just a weird fact of life in the quantum world. Now, prior to the measurement, the wave function might say that the spin axis of the particle could be in any direction. Indeed, the most popular understanding of quantum mechanics says that the spin direction actually is.
So, see that rotating thing on the right-hand side? Let's say that is an encryption key that's going to be transmitted, and nobody knows what it is. And only at some instantaneous point in time is that encryption key locked in a particular direction. And then when that's transmitted, the receiver at the other end is going to know what the encryption key is. But unless somebody was able to lock it in time, which is impossible because these two are entangled, and that third party observing is not entangled with the two. They can't know what the reciprocating state of that encryption key is. Does that making any TMC? Did I go off the deep end there, or did that make any sense?
Yeah, I would only add that when you know the distance to your target, or if you have a moving target, project where they're going to be at any given time, then you will know what the spin or the if you had circular polarization, you would know what that spin state would be when it got to its intended target, and therefore be much more difficult to intercept it midway through flight, because
exactly.
The spin, as well as the energy, as well as the spacing between each respective wave, all will change with distance.
Yep. Remember that other thing too. As soon as you interfere with it, you corrupt it, and it doesn't work.
Right. So when you think about AI and machine learning and quantum computing and all this stuff, right? I'm using those terms just flamboyantly to illustrate that the technology would exist to be able to transmit quantum photons through open space, through a wireless connection, and be able to, with the things I just mentioned, quantum computing and then artificial intelligence and machine learning, you would be able to predict what the states would be at the projected target. You would be able to know that. And so you could build that into your encryption. And you could have the encryption key sort of work both ways, where the receiving end could have an encryption key that would only work if the transmitter sent the right characteristics so that when it was received at the receiver, it would be oriented and lined up, and all of the wave properties that this guy's talking about, many of them.
Right. And if the other characteristics were wrong, then
it wouldn't, the key wouldn't unlock it. It would still be encrypted information. It would be considered corrupt.
That's right.
So any wave interference, any interception, anything would change the properties that were calculated before it was transmitted, so that when it got to the receiving end, even then it would still be unencrypted. You couldn't decrypt it at all. It would be corrupted information.
Yep. Immediately flagged and tagged as corrupted. Right.
It would just be not recognized.
Okay.
And he's talking about one in this example, right? Just the spin. There's many other characteristics that would be built into a quantum encryption. And then you can take multiple beams where you have more than one antenna transmitting at the same time to create a complex helical quantum beam, if you will, that ultimately is part of the key.
There's another place that we didn't even get to, which this is so introductory that it probably won't be dangerous to mention it, but we're talking specifically right now about one qubit, which is one pair of entangled particles. That's called a qubit. I have an article loaded, but we're definitely not going to get to it, where there are multiple qubits. And did you know this, TMC? They're working on circuitry to manufacture multiple entangled qubits. And that fries my brain.
I'd like to see that.
Yeah, I got it. I'll give it to you. We won't do it. We're going to start.
Yeah, please. I'd like to read it.
Okay. Yep. All right. So this isn't too long. Let's let him go. It's good stuff.
In all directions allowed by the wave function. It's only when you make a measurement that the wave function collapses and the outcome becomes real. If you'd like some more information on wave functions and how they collapse.
Notice what he said there. Wave function collapses and it becomes real. So it changes from wave to state, measurable physical state. When it is in its quantum entangled travel, and I use the term travel loosely because this travel happens instantaneously, that is not in a state. That is an energy. It's an energy. And he didn't state that specifically, explicitly, but that's what he means by that. I'll replay that a little bit.
Function. It's only when you make a measurement that the wave function collapses and the outcome becomes real. If you'd like some more information on wave functions and how they collapse, that other video might help. Now, what would happen if you had two subatomic particles? If you're like me, you'd think that they'd both be governed by an individual probabilistic wave function, and they'd be totally independent, with the spin direction of one particle having nothing to do with the spin direction of the other, and both of them being in all directions until a measurement is made. And that happens with four possible outcomes: two wave functions and two probabilities with all combinations of up and down. However, it's possible to prepare two subatomic particles so they both are described by a single wave function. That's what we mean by entangled. Two particles and a single wave function. You do this by taking a parent particle, which in our example has zero spin, and let it decay into two particles. Spin is a conserved quantity, which means that it can never change. So if the parent particle has zero spin, then...
And that segues into, my goodness, it was way back in the chat, but you know who you are when you said it. You nailed it when you said it, that energy is conserved. There's an equal and opposite. And man, it's way back here someplace. But you did say it and you said it right. And you were actually way ahead of our discussion, because that's what this professor is getting to right now. That once that particle decays, in order to conserve energy, one part, they can't have, they can't have the same state, because then it wouldn't be conservation of energy. If one of them is spinning in one direction, the other one must spin in the opposite direction, because they came from a particle that was in a balanced state to begin with. So it's natural. It's completely natural. It's a law that almost can't be violated, that out of one that is at equilibrium are going to come two that are opposite, in order to keep the balance and conserve energy. I don't know if that went over. It's almost goes over my head anyway, but it's that's what he's saying. I'll just play that little bit again too.
And let it decay into two particles. Spin is a conserved quantity, which means that it can never change. So if the parent particle has zero spin, then the two daughter particles have to have opposite spin. If one has a spin pointing left, the other is right. If one is up, the other is down, and so on. When you add the two, you get the zero that you started with.
And there's no in between. There's no in between.
What if you started with something that had a spin?
Then that was already probably I don't know this. I'm guessing that was already entangled with something else.
I think maybe, but I think what would happen is the sum of the daughter particles would equal the spin that it started with as the parent.
We've got to read that multiple qubit patent.
Yeah, that's please send it.
Yep.
Yeah, man, go.
Because they're working on that. Okay.
So that's the simplest example of a pair of entangled particles, which is to say two particles with opposite spin and a single wave function that governs both of them. Okay, so now we're getting somewhere. The entanglement doesn't depend on the two particles being close to one another. As long as the two particles don't interact with anything, you can separate them by feet, miles, or even huge distances, and the two particles are connected by a single wave function, and the two particles will have opposite spin.
What this implies is that the wave function is something that transcends the limit of light speed and distance. It doesn't imply it, it proves it. Well, it's been proven.
Now, remember that one of the key facets of quantum mechanics is that the quantum world is intrinsically probabilistic. We can't know, even in principle, the outcome of a measurement before we make it. So, suppose we select one of the two particles and pick a direction to measure the spin. Say we pick horizontal. The measured spin will be either right or left, each 50% of the time. We could have selected the other particle to do the measurement with the same result, 50% right and 50% left. The real weirdness arises when we measure the spin direction of both of the entangled particles. Say we measure the horizontal spin direction of this particle over here on the left, and the measurement says it's to the right. Then we know that the outcome of the other measurement, it will be 100% of the time left, 100% of the time. That means that the information that one of the two particles had a measurement made on it was transported to the other particle. And here's the spooky thing. We can measure the spin direction of the two particles in quick succession so quickly that we measure the second one before any conceivable information from the first measurement could have arrived.
That's where he's referring to that it transcends the speed of light. Before any possible transmitted information between the left particle and the right particle could have been transmitted by any physical means that we know, the second particle is already in the state that opposes the first particle. That's it right there. That's the crux of it.
Let's be super concrete on this by remembering that the fastest thing in the universe is light. It travels a foot in a billionth of a second. Now, let's take two entangled particles and separate them by 10 feet. It will take light 10 billionths of a second to travel from one to the other. So now let's get tricky. We'll measure the horizontal spin of one of the two particles and see that it's to the right. Then, 5 billionths of a second later, we measure the horizontal spin of the other particle. We find 100% of the time that it's to the left. And remember that we did it so fast that not even light could have told the second particle the outcome of the measurement of the first particle. That means that quantum information can travel faster than light. Yeah, you heard me right. Faster than light. That blew Einstein's mind, too. In fact, he co-authored a paper in 1935 with Boris Podolsky and Nathan Rosen that highlighted this problem. He also called...
So I think we can listen to more of this, but I think that it kind of proves the point that we are living in a universe that has other, there's just, you go through your day, you're looking at the clock, you're saying, okay, I got an hour to do this, I got a half an hour to do that. We live in this very concrete, tangible world. There is a level of reality in our universe. And remember, we live in this universe too, that there are aspects of most likely every part of our body that do not obey the laws of tick, 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 second by second. They don't obey that. That's kind of what this points to, and it's practically proven by some other things that we will talk about again, but we already have. Let's let him go further. This is where they get into the physicists get into a battle here.
This transfer of quantum information, spooky action at a distance. This was one of many reasons why Einstein didn't like quantum mechanics. So what do we think about this phenomenon today? Does quantum information move at speeds faster than light? Yeah, it seems to. But it doesn't invalidate Einstein's theory of relativity because we can't control it. We can make both measurements and the outcome will seem random, and we'll only know that the two were opposite when we compare the measurements, and that information can be transferred no faster than the speed of light. So that saves Einstein's theory, which is a relief. Otherwise, I'd have to learn a whole new bunch of physics. But it's still perplexing. How is it that quantum mechanics can travel so fast? Well, there were some people, including Einstein, who thought that this wasn't so mysterious after all. Suppose that you had a red and a blue ball, but you couldn't look at them. You grab both of them and put them in boxes and separate the boxes. Later, you look in one of the boxes and see that it contains a blue ball. It will surprise nobody that the other ball is red. The answer was determined at the moment the balls were put in the boxes, not when the first ball was observed. And I admit, when I first heard about this, that was pretty much my reaction. The technical name for this more ordinary connection is called hidden variables. So the question is, how do we know?
TMC, wouldn't that imply that the answer was determined when the two particles were generated? I'm just speculating here at this point.
No. It's that all possibilities.
Oh, that's
there.
right. That's right. All possibilities were there. Exactly.
Mm-hmm. And
we live in a universe of all possibilities, folks.
Well, it's a very interesting idea to ponder, that you hear the cliche all the time, oh, follow your dreams, anything is possible, and blah, 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 right? That's, to some extent, it's true.
I mean, think of it, if you were the cat in the box with the stick of dynamite, you're going to be hoping. Am I the one that lives? Am I the one that gets blown up? Follow your dreams, kitty.
Would you know that it's dynamite?
It might not have been dynamite.
Well.
Okay.
I was like, any cat that knows it's dynamite, they picked the wrong cat, man. They should have just picked up a stray and not a genius cat.
That's right. Some cats are smarter than others.
That there is something new and different about quantum mechanics. How can we test the idea of quantum entanglement and compare it to the more intuitive idea of hidden variables? There's a long history of this, with a prediction in 1964 by theorist John Bell and a test in 1981 by Elaine Aspect, as well as contributions by many others. I'm going to forgo the history and the details of the mathematics of the predictions and just explain the measurement. We know that if we measure the spin direction of one particle, that the other one will be in the opposite direction. But let's change it up. Suppose that we measure the spin of the second particle in a totally different direction. How does that change things? Let's measure the direction of the first particle in the vertical direction, but the second one in the horizontal direction. That means that when you measure the spin of the second particle, it will be either right or left. That's weird, but remember, that's how this works for quantum spin measurements. Now, I'm going to simplify the discussion by only talking about the situation when the spin direction measured for the first particle is just up. We could be more general and include both up and down cases, but it's more confusing, and the answer is absolutely identical. If you want to do the general case, let me invoke the phrase that physics professors love and students hate, which is, the exercise is left to the student. Okay, now let's get into both the quantum and hidden variable predictions. The first measurement is in the vertical direction, and it finds the particle has spin up. When you measure the spin of the second, you measure it in the horizontal direction, and you get right and left with equal probability. The first measurement gives you 0 predictive information about the second measurement. It turns out that both quantum mechanics and hidden variables make the same prediction for this scenario. This is very different from if you made the second measurement in the vertical direction, because if you did, you'd get a second measurement in the downward direction 100% of the time. Again, this is the same for both quantum mechanics and hidden variables. So now we're ready for the final bit, which is to look at all possible measurement directions.
So you see what he's doing there. He's laying out the possibility that, well, the scenario where the two particles interact, and that what happens to the second one is still has a communication. It's bidirectional communication. It's basically what he's saying here.
For the second particle, and see if the predictions are different for quantum mechanics and hidden variables. We will still assume that the spin direction measurement for the first particle is upward, and then measure the spin direction for the second particle, starting upward and then slowly spinning the measurement through 360 degrees. This graph shows the predictions of how often the second measurement will be in the direction the second arrow is pointing. If the second arrow is pointing upward, we know that the second measurement is always downward. So that means the second measurement agrees 0% of the time. If the second arrow is pointing at 90 degrees to the right, the second measurement can be right or left with equal probability. So it will be to the right only 50% of the time. If the second arrow is pointing downward, we know that the second measurement always is downward, so it is in that direction 100% of the time. And as we go to 360 degrees, the pattern is reversed. It's very important that we see that the predictions from hidden variables in quantum mechanics are different. This is key. So those are predictions. What does a measurement say? Well, these black dots show the measurement, and they are quite definitive. Quantum mechanics is correct, and the whole idea of hidden variables is completely ruled out. So, what does this mean? It means that the idea that the final measurement is already determined at the moment the two particles is entangled is false. It means that when you measure one of the two particles, the quantum information is transferred to the other particle at a speed faster than light.
Now I understand what he's saying. He's proving, by way of that, he's proving that it is faster than speed of light communications. I couldn't figure out what he was talking about for a minute. Did that register for you?
No, but keep going.
Okay.
Now, with such a provocative statement, you can imagine that there's a lot of discussion. So first, the biggie. No.
Well, he basically showed the proof for what you intuitively said when you refuted what my theory was before we played this last segment. You already had the right answer. You just didn't know how you got it. But he showed you how you could do a proof of it.
Yeah, and I understood what the graphing scheme that he was presenting and this idea of probability. But when he was going through it, like, that's why I watched stuff a couple of times, was when he was going through it, I'm looking at trying to understand how probabilistic computing would be useful when each one of those relationships is tied to a value. And then you start trying to add or manipulate multiple values at the same time and come up with a probabilistic outcome of many different things in a data set. That's where my mind was at. So anyway,
We've waited for a long time to get into this for this exact reason. This is mind-bending stuff.
Great stuff.
Yep. Okay. He's almost done.
Now, with such a provocative statement, you can imagine that there's a lot of discussion. So first, the biggie. No, this does not mean that you can use this to transfer actual information. The collapse of the wave function is still statistical, and it cannot transmit a message. So sorry, we're still stuck with light-speed communication for practical matters. Another feature of this measurement is that scientists have thought very carefully about exactly what it means. There are some ideas, but all are weirder than quantum mechanics. And of course, nobody knows if these ideas are right or not. The bottom line is that, at a minimum, classical physics and hidden variables just don't apply in the quantum world. It's quantum mechanics all the way. The good news is that this new quantum interconnectivity can be useful in such things as quantum computing and quantum teleportation. Did I just come up with a topic for a future video?
Okay, so there you have it. There you have it.
Yeah, he just said that quantum communication wasn't possible.
And I disagree.
Yeah, I think fundamentally what he's saying is it's a fundamental thing. But if you can get the probabilities accurate enough, if you can predict the probabilities accurate enough, you can then apply communication to it. And you're communicating based on probability. The probability of saying the word one instead of the word two, or saying yes versus no. The probability of it.
Also, the initiator and the observer, right? So in the quantum world, the initiator and the observer, as we might look at it with particles or with qubit generating integrated circuits which have been built, the observer and the initiator and the observer are entangled by way of the data or the particles or the qubit being transmitted. They are entangled insofar as the particles, insofar as the qubit that's being transmitted is entangled.
Yeah, I see
and
what you're
that
saying.
all happens faster than the speed of light.
Yeah, and if enough of them were sent in succession, then you could communicate with that for sure.
Yep. Well, last comments from anybody. We're watching the chat, and we're at the end of our time segment, and we're not even going to predict where we're going to go the next time, but it's going to be further, and we want to always relate this to what matters in our lives. You know, you're going to say, well, how does this make any difference to me? And at some levels in our lives, in our very tangible and concrete lives, I might even say in our lives enslaved to this earth that we live on, it really doesn't make much difference at all. But in the hopes and in the distinct possibility of being able to see things at a higher level, at a greater level of consciousness, which would be highly empowering to every individual on this planet, this is the direction in which to go. And we're going to try to pave the way for people to get there. And if you recall, we were speaking about something much more that it hits much more close to home for people when we were speaking about the research done with the Gateway experience, which was from, I think it was 3 weeks ago. Anyway, TMC, last words, and I'm going to take it out. And we want to really thank everybody for being with us. Don't forget to watch other shows on sister channels. One of them is Health Beat on the weekday night at 9 p.m. Eastern. Another one is the wonderful MAGA Ladies, Everything Patriotic from a Lady's Point of View at 9 p.m. on Thursday nights Eastern Time. And you can pretty well count on us being here next Saturday night at 9 p.m. Eastern Time as well. So TMC, take us out, man.
Yeah, we'll see you next week. Come back. This stuff is, this is our future. Well, the faster we understand it, the better off we're going to be.